For over a century, the popular image of astronomy has been a lone scientist peering through an eyepiece in the dark. The reality is quite different. Today, an astronomical discovery looks like hundreds of server racks throwing latency alarms. Astrophysics now operates as a distributed network at the intersection of theoretical physics and petascale computational science. Right now, this hyper-precise, latency-sensitive network is doing something unexpected. The data pipelines streaming from our global observatories are not confirming our foundational models of the cosmos. They are dismantling them in real time. To grasp why the mathematical blueprint of the universe is failing, we first have to examine the sheer scale of the infrastructure built to test it. Cosmology is exiting a multi-decade phase of comfortable agreement. We are entering a period of intense theoretical crisis, driven entirely by compounding, undeniable data. At the center of this crisis is the Lambda Cold Dark Matter model, or Lambda-CDM. For decades, this has served as the undisputed consensus mathematical paradigm of Big Bang cosmology. This framework originated with the gravitational mathematics of Albert Einstein's general theory of relativity in 1915, and gained its observational footing a decade later when Edwin Hubble proved the universe was physically expanding. This timeline illustrates the Lambda-CDM model. The universe begins as a dense singularity, undergoing rapid inflation that seeds quantum fluctuations into a hot primordial plasma. As it expands and cools, stable hydrogen forms. Photons decouple, freezing the density pattern into the cosmic microwave background. Over the next several billion years, gravity compounded those slight overdensities, drawing matter into the vast halos that eventually ignited into the stars, galaxies, and supermassive black holes we observe today. Because this model successfully predicted the large-scale structure of the universe for half a century, these new data anomalies are forcing a total reevaluation of the standard model's core assumptions. The theoretical mechanism of the universe is validated through a massive technological execution model. Ground-based interferometers, like the LIGO Hanford facility, represent the absolute physical limits of this execution. To detect ripples in spacetime, these facilities must measure subatomic strain amplitudes. This means engineering safety constraints to battle continuous terrestrial seismic noise, while simultaneously increasing laser power to overcome the quantum shot noise limit inherent to discrete photons. The incoming strain data feeds directly into the low-latency alert infrastructure. Here, stream-based matched filtering algorithms compare live detector data against a massive bank of waveform templates to identify black hole and neutron star collisions. To handle the massive influx of candidate triggers without exhausting storage or causing system timeouts, the software backend utilizes Kafka-based messaging brokers and Redis database snapshotting. The system's critical performance metric is speed. It achieves a median latency of exactly 9.4 seconds to group candidate triggers into what is classified as a super event. Operating with zero margin for error, this low-latency pipeline relies on purely algorithmic decision-making. Within seconds, it issues a public alert, pivoting optical observatories around the world to capture the fading light of a cosmic collision before it vanishes. When this petascale execution model functions perfectly, it generates data that directly contradicts Lambda-CDM parameters. The first clear failure is the Cosmological Lithium Problem. The physics of Big Bang nucleosynthesis allow us to calculate the exact ratio of light elements, like hydrogen, helium, and lithium, that were generated in the primordial universe. This tracks lithium-7 abundance. The line is the Lambda-CDM prediction. But analysis of old, low-iron stars shows lithium at 1/3 of what the math requires. This contradiction deepens with age. As iron levels drop, lithium plummets to 1/20th of the predicted amount. This deficit forces a difficult choice. Either unknown mechanics inside these stars are actively destroying the lithium, or our foundational assumptions regarding early universe physics are incorrect. The contradictions extend from stellar chemistry up to cosmic topology, largely driven by the near and mid-infrared resolving power of the James Webb Space Telescope. According to standard models, early galaxies emerging from the cosmic dark ages should be small, stable, and slowly assembled into smooth rotating disks over billions of years. JWST observations invalidate this timeline. Data reveals galaxies existing 800 million years after the Big Bang were incredibly massive, violently bright, and highly chaotic. Researchers are finding objects categorized as little red dots. These are galaxies 100 times smaller than the Milky Way, yet they burned with immense energy for 1 billion years. They defy our accepted initial mass function theories, which dictate how stellar brightness correlates to mass. If stars in the early universe burned violently, but lacked the mass our models predict, every existing computational simulation of galactic evolution will have to be rewritten from scratch. But the most severe crisis threatening the entire ΛCDM framework is known as the Hubble tension. The conflict is simple. Measuring expansion using early universe CMB data on the left yields a slow rate. Measuring late universe phenomena on the right yields an accelerated rate. Recent data locked the local rate at 71.6. The numbers don't overlap. The scale breaks. Because of the rigorous automated checks within the data pipeline, we know this discrepancy is a matter of physical reality. It is not an observational error or a calibration mistake. The Hubble tension confirms that the standard model cannot comprehensively map the universe from its origin to its current state. The mathematics physically break between the past and the present. Historically, when instrumentation becomes precise enough to detect persistent anomalies, theorists fall into a specific pattern. Rather than questioning their foundational axioms, they attempt to patch the failing model with increasingly complex, ad hoc mathematical adjustments. But anomalous data is a signal of boundary limits. The Hubble tension cannot be solved by tuning simulation parameters. It requires novel physics. In March 2026, researchers at SLAC ran supercomputer simulations testing this. They modeled early universe plasma with a new variable, the introduction of primordial magnetic fields. By introducing a tiny magnetic force of just 5 to 10 picogauss, a trillionth the strength of a refrigerator magnet, the simulations showed that electrons and neutrons clumped together rapidly. This accelerated recombination, making the universe transparent much earlier than ΛCDM models dictate. This dynamic shrinks the cosmic sound horizon used to measure the CMB. By recalibrating this standard ruler, the resulting Hubble constant aligns with local measurements, suggesting a potential path for resolving the discrepancy. The speed of this theoretical rewrite is being accelerated by a major shift in the astrophysics business ecosystem. A federal mandate has initiated a transition to zero-embargo open data sharing. Traditional 12-month proprietary periods are vanishing. The raw telemetry from JWST and the gravitational wave network is now bypassing institutional silos and flowing directly into the hands of the global academic community. This pipeline will soon expand. Between 2026 and 2035, new wide-field mega-observatories, including the Roman Space Telescope, the Rubin Observatory, and Euclid, will come online, multiplying the volume of cosmological data. The ΛCDM model accurately charted our initial understanding of the cosmos. But exactly like Newtonian physics, we now have the data to show it is merely an effective approximation of a deeper, undiscovered physical law. And the next petabyte of data is about to reveal what that law actually is.